Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The Dutch Republic in the mid-17th century pulsed with intellectual energy, a crucible where commerce, exploration, and scholarly pursuit converged. This era, often termed the Dutch Golden Age, fostered an environment uniquely conducive to scientific inquiry. Wealth generated by global trade funded universities and attracted minds, while practical needs, navigation, cartography, engineering, posed concrete problems, demanding mathematical and physical solutions. It was into this vibrant milieu that Christiaan Huygens was born in 1609, son of Christiaan Huygens, a figure of considerable influence, a diplomat, poet, musician, polymath, deeply embedded in the networks of European intellectual life. Young Christiaan received a privileged education, initially guided by private tutors at home. His father, a friend and correspondent of luminaries such as René Descartes, ensured his son was exposed early to advanced thinking and the burgeoning mechanical philosophy. Constantine recognized Christiaan's precocious mathematical talent and actively nurtured it, introducing him to prominent scholars and facilitating access to contemporary scientific literature. This home environment provided formal instruction and fostered an immersion in the culture of intellectual exploration and critical discourse that defined the era's scientific revolution. Following his home tutelage, Huygens pursued studies in law, the nominal focus at the University of Leiden, and later at the Collegium Aristotelium in Brera. Mathematics and the natural sciences held his deepest interest during this time. The university setting proved valuable, serving as a stepping stone into the wider, informal republic of letters, where the most exciting scientific developments unfolded. The true engine of progress among scholars across Europe at this time was correspondence. Letters served as journals, preprint servers, and discussion forums, carrying problems, proposed solutions, and critiques across national borders. Huygens quickly inserted himself into this vital network. His father's connections proved invaluable, facilitating introductions to key figures. One pivotal early relationship was with Father Mersenne in Paris. Mersenne acted as a central node in the European scientific network, a tireless correspondent who posed challenges and disseminated results from mathematicians like Fermat, Pascal, and Descartes. Huygens began corresponding with Mersenne while still a young man, tackling some of the geometric problems then circulating. This exchange provided Huygens with immediate access to the cutting edge of mathematical thought and forced him to sharpen his analytical skills in difficult, open questions. The mathematical landscape Huygens entered was one of transition. The powerful methods of calculus, later formalized by Newton and Leibniz, awaited full articulation. Mathematicians grappled with problems of motion, areas, volumes, and tangents using ingenious geometric techniques frequently developed for specific cases, drawing inspiration from ancient Greek geometry, particularly Archimedes, and building upon more recent work by figures like Cavalieri with his method of indivisibles. Scholars sought rigorous ways to handle continuous quantities and infinite processes. A particularly challenging and fashionable curve of the mid-17th century was the cycloid. This curve, traced by a point on the circumference of a circle as it rolls along a straight line, possessed a deceptively simple definition and exhibited complex properties. Its study attracted the attention of the era's best minds, including Mersenne, Descartes, Fermat, and Pascal. Problems concerning the cycloid included finding the area enclosed by one arch and the baseline quadrature, determining the slope of the tangent line at any given point, finding its center of gravity, and calculating the length of the curve itself. These problems held practical significance. Understanding such curves proved relevant to mechanics and engineering, particularly in designing gears or analyzing trajectories. Huygens dedicated significant effort to these cycloidal problems during his early period. Working through correspondence with Mersenne and Pascal, he honed his techniques for quadrature and tangency. The method of indivisibles, which treated areas or volumes as composed of infinitely thin slices or lines, provided a powerful heuristic tool, though its logical foundations were still debated. Huygens became adept at manipulating these concepts geometrically to arrive at correct results for areas and volumes of complex shapes. For tangency problems, he employed variations of Fermat's method of adequate differences or Descartes' methods involving normals, essentially early forms of differentiation applied geometrically. His early work on the cycloid, published by the 1651 as theorem order de quadrature hyperboles, ellipsos et circuli ex tora portionem gravitate, encompassed more than the cycloid, showcasing his command of Archimedes methods and indivisibles applied to finding centers of gravity and areas. The underlying challenge involved handling infinitesimal quantities, specifically calculating areas by summing infinitely many lines and finding tangents by considering the limiting position of a secant line. This work occurred before the development of formal calculus notation and limit processes. Huygens demonstrated a remarkable geometric intuition and technical skill in navigating these complexities. His engagement with Pascal over the cycloid in the mid-1650s further solidified his reputation. Pascal famously posed a series of challenges concerning the cycloid's properties. Huygens tackled these problems, contributing to the collective understanding of this enigmatic curve. These exchanges were competitive, pushing participants to develop new geometric arguments and refine existing ones. Huygens' ability to solve these difficult problems, often finding elegant geometric proofs, marked him as a rising star in the mathematical community. These initial mathematical explorations focused on the challenging geometric problems of the day, including quadrature, tangency, and centers of gravity. They served as Huygens' rigorous training ground. They demanded precision, ingenuity, and a deep understanding of classical and contemporary geometric techniques. Grappling with curves like the cycloid, requiring new analytical approaches beyond older methods, forced mathematicians to think in new ways about continuity and change. Huygens' success in this arena demonstrated his exceptional aptitude for mathematical reasoning and laid the groundwork for his later, more revolutionary contributions across a wide spectrum of scientific disciplines. His early immersion in the intellectual ferment of the Dutch Golden Age and his active participation in the European network of scholars provided the fertile ground from which his remarkable career would blossom. These initial mathematical explorations, focused on the challenging geometric problems of the day, quadrature, tangency, centers of gravity, served as Huygens' rigorous training ground. They demanded precision, ingenuity, and a deep understanding of classical and contemporary geometric techniques. Grappling with curves like the cycloid, which resisted easy analysis with older methods, forced mathematicians to think in new ways about continuity and change. Huygens' success in this arena demonstrated his exceptional aptitude for mathematical reasoning and laid the groundwork for his later, more revolutionary contributions across a wide spectrum of scientific disciplines. Moving from the deterministic world of geometry and mechanics, where precise rules dictated outcomes, Huygens turned his formidable intellect towards a realm governed by uncertainty, the analysis of chance. The mid-17th century saw a growing intellectual curiosity about quantifying the likelihood likelihood of events, spurred by practical questions arising from games of chance and wagers. Earlier efforts by mathematicians like Girolamo Cardano involved isolated attempts to analyze dice probabilities. Galileo offered insights into specific problems. A systematic mathematical framework for understanding chance had yet to emerge. The celebrated correspondence between Blaise Pascal and Pierre de Fermat in the 126-150s, prompted by questions from a gambler, Antoine Gambord, the Chevalier de Mireille, had tackled problems like the division of stakes in an interrupted game. This exchange generated powerful insights into combinatorial methods and the concept of expectation. These ideas circulated privately among a select few scholars. A widely accessible, comprehensive theory had yet to be established. Christiaan Huygens entered this intellectual landscape with a unique perspective, shaped by his geometric rigor and his practical engagement with the world. Recognizing the need for a clear, formal language to discuss probability, he undertook the task of structuring these scattered ideas into a coherent, mathematical discipline. His groundbreaking work, published in 156-157, bore the title De Ratiocinalis in Ludo, translating to Calculating in Games of Chance. This slim treatise holds immense historical significance. It stands as the very first published book dedicated entirely to the mathematical theory of probability. Huygens' approach into Ratiocinalis was systematic and axiomatic, beginning with fundamental definitions and proceeding through logical propositions. He aimed to provide a method for determining the equitable value of a contingent expectation, essentially calculating what a future uncertain payoff was worth now. The core concept he introduced and formalized was what he termed expectatio, or expectation. He defined the expectation of a person in a game as the value of their chance at winning a particular sum. If one had an equal chance of winning sum A or sum B, the expectation was the arithmetic mean of A and B, expressed as a plus B divided by 2. This was a profound step, providing a quantitative measure for the value of an uncertain prospect. Huygens expanded this definition to encompass situations with multiple possible outcomes, each with a defined probability. If there were P chances of winning sum A and Q chances of winning sum B, the expectation was calculated as P times A plus Q times B, all divided by P plus Q. This formula, expressed using modern notation as E equals the sum of the probability of each outcome multiplied by its value, forms the bedrock of the concept of expected value, a cornerstone of probability theory and its myriad applications today. The treatise De Ratiocinalis then applied this concept of expectation to a series of progressively complex problems derived from popular games of chance of the era, such as dice games involving multiple throws and players, and problems concerning the drawing of balls from urns. Huygens meticulously worked through these examples, demonstrating how to calculate expectations in various scenarios. He showed how to determine the probability of specific outcomes in multiple dice rolls, how to value a player's position if a game were interrupted, and how to analyze the fairness of different betting structures. His methods, routed in combinatorial reasoning akin to Pascal and Fermat, possessed a clarity and structure that made them accessible to a wider audience and provided a template for future probabilistic investigations. One particularly significant problem addressed by Huygens involved calculating the probability of throwing a specific sum with multiple dice. For instance, determining the chance of throwing a total of 7 with 2 dice. He systematically enumerated the favorable outcomes 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, and related them to the total possible outcomes 6 times 6, or 36, arriving at the probability of 6/36, or 1/6. While seemingly simple to us now, this systematic enumeration and calculation of probabilities for specific events within a defined sample space was fundamental to establishing probability as a rigorous mathematical field. Another classic problem Huygens tackled involved the division of stakes in an unfinished game. If two players, say A and B, are playing a game where the first to reach a certain number of points wins the entire stake, and the game is interrupted before either player reaches the target, how should the total stake be divided fairly based on their current scores? Huygens' solution, building on the ideas of Pascal and Fermat, involved calculating each player's probability of winning the game from that point forward, assuming play were to continue. The stakes would then be divided in proportion to these probabilities. This problem, known as the problem of points, became a foundational example in probability, illustrating how to assess future probabilities based on current states and how to use those probabilities to determine fair value. Huygens' explicit presentation of the solution in his published work made this crucial insight widely known. The significance of De Ratiocinalis and Ludo extends far beyond the gaming table. By providing the first formal, published framework for calculating expectations and probabilities, Huygens gave mathematicians and thinkers the tools to analyze uncertainty in a quantitative manner. This treatise served as a standard text on probability for half a century, influencing subsequent giants in the field. James Bernoulli, in his posthumously published Ars Conjectandi, the Art of Conjecturing in 1007-113, which contained the first version of the law of large numbers, explicitly built upon Huygens' work, reprinting De Ratiocinalis as the first part of his own treatise. Abraham de Moivre, another key figure in early probability, also acknowledged his debt to Huygens. The concept of expected value, introduced and formalized by Huygens, permeates countless aspects of modern life, is fundamental to the theory of statistics, underpinning methods for estimation, hypothesis testing, and data analysis. It forms the mathematical core of actuarial science, allowing insurance companies to quantify risk and set premiums based on the expected costs of future claims. The mathematics that allows these companies to bet on our collective longevity and usually win in finance. Expected value is a critical tool for valuing assets, assessing investment strategies, and managing risk in portfolios. Modern quantitative finance, with its complex models for pricing derivatives and managing market exposure, traces a direct lineage back to Huygens' initial efforts to quantify the value of a future uncertain sum. Decision theory, which seeks to provide a rational framework for making choices under uncertainty, relies heavily on the concept of maximizing expected utility, a direct descendant of Huygens' expectation. Huygens' work in probability theory stands as a testament to his ability to translate practical problems into rigorous mathematical structures. He perceived the underlying mathematical principles governing chance events and provided the language and tools to analyze them systematically. His treatise, born from the analysis of dice games, provided the crucial spark that ignited the formal study of probability, a field that has grown to become indispensable across science, economics, and everyday decision-making. This foundational contribution to abstract mathematical theory, derived from seemingly trivial beginnings, exemplifies the interconnectedness of intellectual curiosity and practical application that characterized Huygens' genius. Moving from those abstract calculations of chance, Christiaan Huygens' attention would also turn to the physical world, seeking to improve humanity's ability to observe the cosmos and understand the nature of light. The burgeoning field of astronomy in the mid-17th century presented profound challenges, foremost among them the limitations imposed by the very instruments available. Refracting telescopes, which used lenses to gather and focus light, suffered from inherent optical defects that severely restricted their power and clarity. Two principal culprits plagued these early instruments: chromatic aberration and spherical aberration. Chromatic aberration arose from the fundamental property of glass that causes different colors of light to bend at slightly different angles when passing through a lens. This phenomenon meant that a single lens could bring red light to focus at one point, focusing blue light at a slightly different point. The result was a blurred image surrounded by distracting fringes of color, particularly noticeable at the edges of the field of view and around bright objects like stars and planets. This defect impeded the discernment of fine details and rendered high magnifications hopelessly muddled. Spherical aberrations stemmed from the shape of the lens itself. A simple spherical surface, easier to grind than an ideal parabolic one, fails to bring all incoming parallel rays of light to a single, precise focal point. Rays passing through the edge of a spherical lens focus closer to the lens than rays passing through the center. This spread of focal points smeared the image, reducing sharpness and contrast. While lens makers understood the theoretical advantage of parabolic surfaces for eliminating spherical aberration, the practical difficulty of grinding such shapes accurately, especially for larger lenses, remained a significant hurdle. These optical imperfections meant that increasing the size of the objective lens to gather more light, or increasing magnification by using shorter focal length eyepieces, often exacerbated the problems, leading to larger, blurrier, and more colorful images, diminishing clarity. Astronomers were thus caught in a bind, desiring greater light gathering power and magnification to see fainter and more distant objects, yet finding their efforts undermined by the very physics of light and glass. Huygens, possessing both a deep theoretical understanding of optics and a remarkable practical aptitude for craftsmanship, tackled these problems head-on. He recognized that building bigger telescopes with the same flawed lens technology offered diminishing returns. His approach involved improving the fundamental components and configurations of the telescope. A crucial part of his contribution lay in the meticulous art of lens grinding and polishing. Huygens, along with his brother Constantin, devoted considerable time and effort to perfecting the techniques for creating lenses with smoother surfaces and more accurate shapes. They developed improved methods for polishing lenses, achieving a higher degree of precision than was common at the time. This allowed them to produce subjective lenses with better figure, reducing the impact of spherical aberration compared to lenses made with less refined methods. While achieving perfect parabolic surfaces remained beyond the technology of the era for large lenses, their superior grinding techniques yielded lenses that were closer to the ideal shape and had fewer surface imperfections. Huygens made significant advancements in eyepiece design. Simple telescopes typically used a single lens as the eyepiece, which introduced significant chromatic aberration and limited the field of view. Huygens designed a two-lens eyepiece that became known as the Huygens eyepiece. This design consisted of two plano-convex lenses placed with their plane sides facing the eye. The key innovation lay in the specific separation of these two lenses. Huygens determined that by placing the field lens, the one closer to the objective, and the eye lens, the one closer to the eye, a distance apart equal to half the sum of their focal lengths, he could significantly reduce chromatic aberration and provide a wider, flatter field of view. The first lens, the field lens, intercepted the light rays from the objective before they came to a complete focus. It bent the rays inward towards the second lens, the eye lens. The eye lens then took these converging rays and directed them into the observer's eye as a parallel beam, creating a magnified image. The clever arrangement of the two lenses and their separation meant that the chromatic dispersion introduced by the first lens was partially compensated by the second lens. The Huygens eyepiece offered a dramatic improvement. It provided clearer views with reduced distortion across a larger portion of the image, significantly mitigating color fringing. This design proved so effective that variations of the Huygens eyepiece remained standard in telescopes and other optical instruments for centuries. Huygens also understood a principle related to chromatic aberration that would heavily influence telescope design during this period. For a given objective lens diameter, aperture, the amount of chromatic aberration introduced decreases as the focal length increases. This meant that building telescopes with very long focal lengths relative to their aperture could minimize the detrimental effects of color fringing. The longer the focal length, the less the light had to be bent by the lens, and thus the less the different colors were separated. This understanding led to the era of the long telescopes. Astronomers began constructing instruments with focal lengths of 20, 50, or even 100 feet. These extremely long tubes offered assistance in mitigating chromatic aberration. Concurrently, they presented immense practical problems. The tubes were heavy, difficult to maneuver, prone to flexing and vibrating in the wind, and required elaborate scaffolding or masts to support them. Aiming them accurately at celestial objects became a significant challenge. Huygens devised an ingenious solution to the unwieldiness of these extremely long tubes of the aerial telescope. He realized that the tube itself served primarily to hold the objective, an eyepiece, at the correct distance and to keep stray light out. He reasoned that attaining the correct separation and alignment through alternative means independent of a physical tube would allow overcoming many practical difficulties. His aerial telescope design involved mounting the objective lens at the top of a tall pole or on a building, sometimes using a swivel joint to allow it to be pointed. The eyepiece was held by the observer at ground level or on a separate stand, and the two components were aligned using a taut string or rod connecting them, sometimes incorporating aiming sights. This radical approach to telescope construction enabled the use of objective lenses with focal lengths far exceeding practical limits imposed by tubes. Huygens and others built and used aerial telescopes with focal lengths reaching 120 feet or even more. Operating these instruments demanded considerable skill. They provided unprecedented clarity and magnification for the time. Their design effectively addressed the limitations imposed by tube construction. This approach leveraged the principle that long focal lengths reduced chromatic aberration. Huygens' work in optics and telescope design thus represented a multifaceted attack on the problems limiting astronomical observation. He improved the quality of the fundamental components through better lens grinding, enhanced the eyepiece to provide clearer, wider views, and innovated the overall telescope structure to enable the use of optically superior long focal length objectives. These advancements combined a strong theoretical basis with deep roots in practical craftsmanship and engineering ingenuity. The precision he brought to lens making and the clever design of his eyepiece significantly improved the performance of refracting telescopes, making clearer and more detailed observations possible. The aerial telescope, while eventually superseded by later inventions like the abermatic lens, represented a brilliant, if demanding, solution to the pressing problem of chromatic aberration in the era of long telescopes. These optical contributions laid the groundwork for a new era of astronomical discovery, allowing observers to peer into the heavens with previously unattainable clarity. The instruments built and designed by Huygens would soon reveal secrets of the cosmos that had remained hidden from earlier generations of astronomers, secrets that his keen eye and analytical mind were uniquely prepared to interpret. Equipped with the superior optical instruments he had meticulously designed and constructed, instruments born from a profound understanding of lens properties and an unwavering commitment to precision craftsmanship, Christiaan Huygens turned his gaze towards the heavens. The era was one of burgeoning telescopic observation, a time when the universe, previously a realm of philosophical speculation illuminated by naked eye astronomy, was beginning to reveal its mechanical secrets through glass lenses. Yet, even with the advent of the telescope, the view presented limitations for many phenomena. Galileo Galilei, the pioneering observer, had glimpsed strange appendages flanking the planet Saturn, describing them as ears or companion bodies, but their ephemeral nature and changing appearance presented a complex puzzle. Other observers offered equally perplexing descriptions, including arms, handles, or even a triple planet. The true nature of Saturn's peculiar form remained one of the most tantalizing enigmas of the mid-17th century, a visual puzzle that challenged the prevailing understanding of planetary structure. Huygens approached this problem with a distinct advantage, employing telescopes possessing significantly greater resolving power and clarity than those available to his predecessors. His long focal length objectives, coupled with refined eyepieces, cut through the atmospheric distortion and chromatic aberration that plagued earlier instruments, presenting planetary discs with unprecedented sharpness. He began a systematic study of Saturn, observing it repeatedly over several years, meticulously documenting its changing appearance. These observations commenced in earnest around 1655, as the planet orbited the sun and Earth's perspective changed. A shape shape of the appendages seemed to morph in a way consistent with a specific structural form. They would shrink, sometimes disappear entirely, and then reappear, changing their angle relative to the planet's disk. This dynamic behavior was a critical clue. Huygens brought to bear his formidable geometric intellect upon these observations. He reasoned that if the appendages were solid bodies orbiting Saturn, their appearance should remain consistent relative to the planet itself, exhibiting only the predictable changes associated with orbital motion and phase. The observed changes, however, suggested something else entirely, a single, continuous structure encircling the planet, viewed at varying angles as Earth and Saturn moved in their respective orbits. This structure, he hypothesized, must be remarkably thin and flat, oriented in a plane inclined to Earth's orbital plane. His unique solution to the Saturnian enigma was articulated in his 1659 treatise, Systema Saturniana. He proposed that Saturn was surrounded by a thin, flat ring nowhere touching the planet itself. He used careful diagrams to illustrate how such a ring, when viewed from different angles over time, would perfectly account for the observed changes in appearance, including the moments when the ring appeared edge-on and became invisible, or when the Earth passed through the plane of the ring. This geometric model provided a complete and internally consistent explanation for all puzzling observations made over decades. The ring hypothesis was audacious, proposing a structure unlike anything else seen in the solar system Earthlings knew, yet it possessed the compelling power of predictive accuracy. It explained the past observations and allowed for predictions of future appearances. The clarity of his observations and the elegance of his geometric explanation convinced the scientific community. The years of Galileo were transformed into a majestic ring system, a discovery that fundamentally altered the perception of planetary architecture. It demonstrated that planets could possess complex, previously unimagined features. This discovery served as a powerful testament to the efficacy of combining superior instrumentation with rigorous mathematical and geometric analysis. It showcased how empirical observation, when interpreted through the lens of precise geometric reasoning, could unlock profound secrets of the cosmos. During these same meticulous observations of Saturn, Huygens made another significant discovery. On March 25, 1655, using one of his finest telescopes, he detected a bright point of light orbiting Saturn, located outside the ring structure. This body exhibited orbital motion around the planet, confirming its status as a satellite. He tracked its movement over several weeks, confirming its period and orbital path. He initially announced its discovery cryptically using an anagram to secure priority, while he gathered more data. Once confident, he revealed his finding Saturn possessed a moon. He named his moon Titan, drawing from Greek mythology, where the Titans were siblings of Saturn. Titan was the first moon found orbiting Saturn, and the sixth moon discovered in the solar system orbiting a planet. The previous discoveries were Galileo's four large moons of Jupiter, Io, Europa, Ganymede, and Callisto, observed decades earlier. Huygens' discovery of Titan further expanded the known inventory of solar system bodies and provided additional evidence that planets could host their own satellite systems, reinforcing the idea of the solar system as a collection of diverse planetary systems. These astronomical triumphs, the identification of Saturn's rings, and the discovery of Titan were direct consequences of the optical advancements described previously. They validated the immense effort Huygens invested in creating better telescopes. The problems they addressed were the fundamental challenges of observational astronomy at the time, achieving sufficient resolution to distinguish fine details on distant objects, and interpreting those details correctly in 3 dimensions based on 2-dimensional telescopic views. Huygens' unique solutions involved pushing the boundaries of optical technology and applying sophisticated geometric models to observational data. The modern relevance of these discoveries remains profound. Saturn's rings are now understood as an intricate system of countless icy particles, a structure exceeding Huygens' imaginings. Nevertheless, his fundamental insight into their nature as a flat, thin ring system encircling the planet retains its validity. Modern space probes, including the Cassini-Huygens mission, partially named in his honor, have revealed Titan as a world of extraordinary interest, possessing a dense atmosphere and liquid methane lakes. This complexity builds upon the initial detection made by Huygens. His work initiated the detailed study of the Saturnian system, a field that continues to yield astonishing discoveries. Huygens' astronomical contributions underscored a crucial principle: progress in understanding the universe is intimately linked to the quality of our instruments and the rigor of our interpretation. His observations of Saturn and Titan were milestones in planetary astronomy, expanding the focus beyond merely cataloging celestial bodies to encompass understanding their physical structure and dynamics. They demonstrated the power of empirical observation guided by theoretical insight, setting a standard for future astronomical research. The need to precisely track the movements of these newly discovered moons and the complex, changing appearance of Saturn's rings highlighted a growing requirement for accurate timekeeping in astronomical observation, a challenge that would soon occupy a significant portion of Huygens' intellectual energy. The pursuit of celestial knowledge, as Christiaan Huygens' own Saturnian discoveries demonstrated, underscored a profound, earthbound challenge. Precisely tracking the movements of celestial bodies, conducting rigorous physical experiments, and navigating the vast oceans demanded a level of temporal accuracy far exceeding the capabilities of mechanical clocks then in use. These instruments, typically driven by falling weights or coiled springs, relied on mechanisms like the foliot escapement, which struggled to deliver energy consistently and were highly susceptible to variations in driving force, friction, and temperature. Their timekeeping was inherently unstable, drifting significantly over short periods. This instability prevented their use for observations requiring synchronized measurements or for the critical task of determining longitude at sea, which relied directly on comparing local time with the time at a reference meridian. Christiaan Huygens recognized this fundamental limitation as a barrier to scientific progress and maritime safety. He sought a reliable, natural phenomenon that could provide a stable rhythm, a consistent pulse to regulate the flow of time in a mechanical device. His attention turned to the pendulum, a body swinging freely under the influence of gravity. Galileo Galilei had earlier observed a remarkable property of the pendulum: its period of swing remained approximately constant, regardless of the amplitude of the swing, provided the swings were small. This property, termed isochronism, offered the potential for a far more accurate timekeeping standard than any existing mechanical oscillator. Huygens embarked on the ambitious project of harnessing the pendulum's steady beat to drive a clock. This required inventing a new mechanism to interface the continuous back-and-forth motion of the pendulum with the unidirectional, stepwise movement of the clock's gear train. This mechanism, the escapement, needed to serve 2 crucial functions simultaneously. It had to allow the gear train to advance by a fixed amount with each swing of the pendulum, effectively counting the oscillations, and it had to provide a small impulse to the pendulum on each swing to counteract energy losses due to air resistance and friction, thereby keeping the pendulum swinging. Huygens' ingenious solution involved a verge escapement connected to a pendulum, a design he patented in 1657. The introduction of the pendulum clock marked a revolution in timekeeping. For the first time, clocks achieved an accuracy previously unimaginable, improving precision by orders of magnitude. A good pendulum clock could keep time to within a minute a day, a vast improvement over the quarter hour or more lost daily by earlier clocks. This newfound precision immediately benefited astronomers, allowing for more accurate timing of celestial events and better tracking of planetary motions. Scientists could now perform experiments involving duration with unprecedented reliability. Huygens extended his efforts beyond the invention itself. He undertook a deep theoretical investigation into the physics of oscillation, culminating in his monumental treatise, Horology, Oscillatorium side to Pendulum ad Horologer, a total demonstrations geometrique published in Paris in 1673. This work stands as one of the most significant books on mechanics of the 17th century, a masterpiece of mathematical physics. In Horologium Oscillatorium, Huygens presented a comprehensive mathematical analysis of the pendulum. He rigorously precisely derived the formula for the period of a simple pendulum, demonstrating its dependence on the square root of its length and the acceleration due to gravity. He also tackled the problem of the compound pendulum, a more complex system involving extended bodies, determining its center of oscillation. He addressed the limitation of Galileo's observation, the perfect isochronism of a simple pendulum holds strictly only for infinitesimally small swings. For larger amplitudes, the period increases slightly, introducing inaccuracy. Seeking a curve along which a pendulum would be perfectly isochronous for any amplitude, Huygens discovered the properties of the cycloid. He proved that the volute of a cycloid is another cycloid. Furthermore, he demonstrated that if a pendulum bob is constrained to swing along a cycloidal path by suspending it from flexible strips that wrap around cycloidal cheeks, its period is independent of the amplitude of the swing. This property makes the cycloid a tautochromic curve along which a particle will descend to the lowest point in the same amount of time, regardless of its starting position. While building clocks with cycloidal pendulums proved technically challenging and offered diminishing returns compared to the practical difficulties, Huygens' theoretical discovery was profound. It represented one of the earliest solutions to a significant problem in dynamics using advanced geometrical and analytical techniques, showcasing the power of mathematics to reveal deep physical truths. Horology Oscillatorium detailed the theory of oscillating systems, explored the concept of the center of oscillation, and provided extensive practical information on the design and construction of pendulum clocks. It was a foundational text that disseminated the principles of accurate mechanical timekeeping throughout Europe. While the pendulum clock revolutionized stationary timekeeping, the instability of a pendulum on a moving platform, particularly a ship at sea, remained a significant hurdle for solving the longitude problem. Huygens turned his attention to alternative regulators. He experimented with using a balance wheel combined with a spring, seeking an oscillator whose period was independent of its orientation. In Budget 675, he developed a functional balance spring mechanism for watches and portable timekeepers. This invention provided the basis for accurate pocket watches and, eventually, marine chronometers, though the latter required decades of further refinement by clockmakers like John Harrison to achieve the necessary precision for reliable navigation at sea. Huygens' contributions to horology fundamentally transformed scientific measurement and navigation. The ability to measure time accurately provided a critical tool for empirical science, enabling detailed studies of motion, gravity, and astronomical phenomena. The principles he elucidated concerning oscillation, resonance, and the design of mechanical regulators became cornerstones of engineering and physics. Even in the age of atomic clocks, the concepts of stable oscillation and precise mechanical control, pioneered by Huygens, remain relevant in various mechanical and electronic systems. His work elevated clockmaking from a craft to a science, demonstrating the power of applying rigorous mathematical and physical principles to solve practical problems. The precision and timekeeping Christiaan Huygens introduced would prove indispensable for the increasingly sophisticated physical investigations that would occupy his attention in subsequent years, particularly his studies of motion and the nature of light. His analytical mind, honed by years of rigorous mathematical study and practical engineering, sought to bring clarity and order to the fundamental interactions of the physical world. The dynamics of colliding bodies, a seemingly straightforward problem, presented a puzzle that had eluded even the most brilliant minds of the era. René Descartes, a towering figure whose philosophical and scientific system dominated much of 17th century thought, had proposed a set of rules governing the outcomes of collisions. These rules, embedded within his comprehensive physics, were widely accepted despite containing fundamental inaccuracies. Descartes' system offered a compelling mechanistic view of the universe. It struggled to correctly predict the behavior of bodies after impact, particularly concerning the conservation of momentum, or what was then understood as quantity of motion. His rules, for instance, sometimes implied that a smaller body striking a larger one could reverse the motion of the larger body, while the smaller body maintained its original direction, a scenario contradicted by observation. The problem demanded a more rigorous, mathematically sound approach, one that accounted for the observed behavior of colliding objects with precision. Huygens tackled this problem with characteristic ingenuity, employing a method that implicitly utilized a Galilean principle of relativity centuries before its formal articulation. He considered collisions from the perspective of different inertial frames of reference. By analyzing the collision of two bodies from the viewpoint of an observer moving with one of the bodies, Huygens could simplify the problem and deduce the correct laws governing the speeds and directions of the bodies after impact. This relative velocity approach allowed him to bypass the complexities that had ensnared Descartes. He discovered that for elastic collisions, impacts where kinetic energy is conserved, there existed a consistent relationship between the relative velocities of the bodies before and after the collision. The relative velocity after impact possessed the same magnitude as the relative velocity before impact, differing solely in direction. His analysis revealed that the total momentum of the system is sum of the product of each body's mass and velocity remained constant throughout the collision. Huygens derived rules of collision were mathematically equivalent to the fundamental principle of momentum conservation for elastic impacts. He articulated the concept in a manner preceding its modern explicit statement. His work provided the first correct mathematical description of elastic collisions, a foundational element of classical mechanics. This achievement was significant because it provided a set of rules that actually worked, accurately predicting outcomes Descartes' rules were insufficient to predict. His insights into collisions formed a cornerstone of the emerging science of dynamics, providing physicists with a reliable framework for analyzing interactions between bodies. These principles remain fundamental to the study of mechanics today, taught in introductory physics courses and applied in fields ranging from engineering to astrophysics. The analysis of collisions, whether elastic or inelastic, relies directly on the conservation principles that Huygens' work implicitly validated and helped establish. Huygens' intellectual gaze, having addressed the mechanics of tangible bodies, turned towards the most ethereal and mysterious phenomenon known, light. The nature of light had been a subject of intense philosophical and scientific debate for centuries. The prevailing view, championed prominently by Isaac Newton, posited that light comprised tiny particles or corpuscles emitted from luminous sources. This corpuscular theory offered compelling explanations for phenomena like reflection, where light particles were imagined to bounce off surfaces like tiny balls, and refraction, explained by particles changing speed as they entered different media. Yet, as observations became more refined, certain behaviors of light presented considerable difficulties for the particle model. Phenomena involving the bending of light around obstacles, diffraction, and the complex patterns created when light beams overlapped interference proved particularly challenging to explain solely through the motion of particles. A deeper understanding of light's fundamental character was needed, one that could unify these disparate observations under a single, coherent framework. Huygens proposed a radically different conception, light as a wave. He hypothesized that light consisted of disturbances propagating through a ubiquitous, invisible medium he called the luminiferous ether, which was thought to permeate all space, including vacuums. According to this wave theory, light sources emitted waves that spread out in all directions, analogous to ripples on the surface of water. This wave model offered elegant explanations for reflection and refraction. Reflection could be understood as waves bouncing off a boundary, obeying the law of equal angles. Refraction was explained by the change in the wave's speed as it passed from one medium to another, causing the wave front to bend. This explanation provided a quantitative link between the refractive index of a material and the speed of light within it, a prediction that differed from the corpuscular theory and would later be subject to experimental verification. To describe how these waves propagated, Huygens introduced a powerful geometric construction known today as Huygens' principle. This principle states that every point on a propagating wave front can be considered as the source of secondary spherical wavelets. The new wave front at a later time is then the envelope, the tangent surface of all these secondary wavelets. This principle provided a simple yet effective method for predicting the shape and position of a wave front as it moved through space or encountered obstacles or boundaries. It offered a visual and intuitive way to understand how waves spread, bend, and interact. Using this principle, Huygens could geometrically derive the laws of reflection and refraction, demonstrating the explanatory power of his wave model. Huygens' wave theory provided elegant explanations for known phenomena and offered a potential framework for understanding others. It faced significant challenges to widespread acceptance. The concept of a luminiferous ether was speculative and difficult to reconcile with the apparent emptiness of space. Furthermore, the wave theory initially found explaining polarization challenging. Directed particles accounted for this phenomenon effectively. Crucially, the immense authority and influence of Isaac Newton, who remained a staunch advocate of the corpuscular theory, meant that Huygens' wave model was largely overshadowed for over a century. Newton's optics, with its detailed experiments and powerful arguments for the particle nature of light, became the dominant paradigm. The wave theory possessed an inherent explanatory power for phenomena the particle theory accommodated with difficulty as experimental techniques improved and new observations were made, particularly in the early 19th century, by figures like Thomas Young and Augustin Jean Fresnel. The evidence for the wave nature of light became increasingly compelling. Their experiments on interference and diffraction provided quantitative support for Huygens' fundamental idea. Fresnel, in particular, refined Huygens' principle, demonstrating its ability to predict complex diffraction patterns with remarkable accuracy. Huygens' wave theory, initially receiving limited attention, ultimately proved foundational for the modern understanding of light. It paved the way for James Clerk Maxwell's electromagnetic theory of light, which identified light waves as propagating oscillations of electric and magnetic fields, dispensing with the need for mechanical ether. Even in the context of quantum mechanics, where light exhibits both wave-like and particle-like properties, wave-particle duality, the wave description remains essential for understanding phenomena involving propagation and interference. Huygens' pioneering work established the conceptual framework for thinking about light as a wave, a perspective that continues to inform physics today. His investigations into the dynamics of collisions provided essential tools for analyzing mechanical systems. His bold proposal of the wave theory of light offered a revolutionary paradigm that would eventually transform our understanding of the universe's most fundamental interactions. These contributions represent profound extensions of his relentless pursuit of mathematical clarity in describing the physical world, building upon the foundation of precise measurement enabled by his horological innovations. Christiaan Huygens' intellectual reach extended across a remarkable spectrum of scientific inquiry, touching upon areas that might seem disparate at first glance, yet were unified by his characteristic approach applying rigorous mathematical analysis to phenomena observed through careful experimentation and often facilitated by instruments of his own design. Consider, for instance, his work on centrifugal force. While others had grappled with the forces involved in circular motion, Huygens provided a precise mathematical formulation. He derived the expression for the centrifugal force acting on a body moving in a circle, showing it to be proportional to the square of the velocity and inversely proportional to the radius of the circle. This result, often expressed today as mv squared divided by r, where m is mass, v is velocity, and r is radius, was a crucial piece in understanding mechanics, essential for everything from planetary orbits to the design of machinery. His analysis here exemplifies his method: identify a physical problem, devise an experimental setup or thought experiment to isolate the forces, and then apply geometry and nascent calculus to arrive at a quantitative description. Beyond fundamental mechanics, his inventive spirit manifested in practical devices. He developed improvements to the air pump, a vital tool for studying vacuums and air pressure, and designed a manometer, an instrument for measuring pressure. These underscore a critical aspect of his genius: the seamless integration of theoretical insight with practical engineering. He perceived that advancing scientific understanding demanded better tools for observation and measurement, and he possessed the skill and ingenuity to create them. His work on the manometer, for example, contributed to the growing understanding of fluid mechanics and atmospheric pressure fields that were rapidly developing in the wake of Torricelli's experiments. Huygens operated within and helped shape the burgeoning international scientific community of the 17th century. Science was increasingly becoming a collaborative, albeit competitive, endeavor conducted through correspondence, publications, and formal academies. His extended stay in Paris, commencing in the late 1660s, positioned him centrally within this network. Jean-Baptiste Collet, the influential minister of Louis XIV, extended an invitation, leading Huygens to become a foundational member of the French Royal Academy of Sciences. This academy furnished him with resources, a salary, and an environment conducive to research and discourse. His involvement conferred considerable prestige upon the nascent academy, and he actively participated in its initial endeavors, presenting his findings on collisions, optics, and related topics to his colleagues. His exchanges with other prominent individuals proved crucial. His correspondence with Gottfried Wilhelm Leibniz, for instance, addressed mathematics, mechanics, and philosophy. As Leibniz developed his unique formulation of calculus, separate from Newton's, his conversations with Huygens offered fertile intellectual ground. Huygens, consistently favoring rigorous geometry, initially regarded the novel calculus techniques with some reservation, preferring the lucidity of classical geometric demonstrations. Nevertheless, he acknowledged their efficacy and collaborated with Leibniz on foundational principles of dynamics, specifically the notion of vis viva, or living force, which relates to kinetic energy. This concept represented a divergence from Descartes' views, and Huygens explored it mathematically. His association with Isaac Newton was multifaceted, characterized by mutual esteem, intellectual divergences, and the prevailing undertones of priority disputes common to that period. They exchanged correspondence concerning optics, particularly the fundamental nature of light. While Newton advocated for the corpuscular or particle theory, Huygens maintained his firm support for his wave theory. The contrasting perspectives on light precipitated notable discussions conveyed through letters and published works. Huygens, for example, offered critiques of Newton's experiments on color dispersion, proposing alternative explanations rooted in his wave model. Notwithstanding their theoretical divergences regarding optics, they shared a collective dedication to mathematical physics and empirical validation. Huygens acknowledged Newton's profound contributions to mechanics, particularly the laws of motion and universal gravitation. He initially expressed reservations about the concept of action at a distance inherent in Newtonian gravity, seeking a more mechanistic explanation. The synthesis of Huygens' work reveals a mind of extraordinary breadth and depth. He was a mathematician who applied his skills to physical problems, a physicist who demanded experimental verification and quantitative precision, and an engineer who built the instruments necessary for both. His contributions spanned mathematics, physics, astronomy, horology, and technology. He approached each field with clarity of thought, mathematical rigor, and reliance on empirical evidence. In mathematics, his work on probability laid foundational stones for a field that permeates modern science, finance, and statistics. His geometrical methods, while eventually superseded by calculus, demonstrated the power of rigorous proof and analytical thinking applied to curves and surfaces. In physics, his analysis of collisions was crucial for the development of mechanics, contributing to the understanding of conservation principles. His work on centrifugal force was a key component in the development of classical mechanics, underpinning our understanding of rotational motion and orbital dynamics. His most revolutionary contribution to physics, the wave theory of light, faced considerable resistance initially, overshadowed by Newton's authority. Yet, it contained contained the seeds of future triumphs. Thomas Young's double-slit experiment in the early 19th century provided compelling evidence for the wave nature of light, and Augustin Jean Fresnel later developed the mathematical framework that fully realized Huygens' principle, explaining diffraction and interference phenomena with remarkable accuracy. Maxwell's electromagnetic theory solidified light's identity as an electromagnetic wave, a concept deeply rooted in the wave paradigm Huygens championed. Even with the advent of quantum mechanics and the concept of photons, the wave description remains indispensable for understanding a vast range of optical phenomena. In astronomy, his improvements to the telescope and his discoveries of Saturn's rings and Titan showcase the power of enhanced instrumentation and careful observation. His determination of the distance to Sirius, though based on assumptions that proved inaccurate, represented an early, systematic attempt to measure interstellar distances, pushing the boundaries of astronomical inquiry. The pendulum clock, perhaps his most celebrated invention in his own time, transformed measurement. It provided the first reliable means of measuring time accurately, revolutionizing scientific experimentation, navigation, and daily life. This invention alone would secure his place in history. It was one facet of his relentless drive to understand and quantify the physical world. Huygens occupies a unique and pivotal position within the scientific revolution. He bridged the gap between the geometrical methods of the past and the analytical techniques of the future. He embodied the ideal of a natural philosopher who was simultaneously a theoretician, an experimentalist, and an inventor. He stood alongside figures like Descartes, Galileo, Newton, and Leibniz, contributing fundamental ideas and techniques that shaped the course of modern science. His scientific spirit endures as a model of intellectual integrity and persistent inquiry. He pursued truth with unwavering rigor, unafraid to challenge conventional wisdom, as seen in his advocacy for the wave theory of light against prevailing opinion. He understood that progress in science depended upon a harmonious interplay between abstract mathematical reasoning and concrete empirical investigation. His life's work stands as a testament to the power of applying sharp mathematical tools to the intricate workings of the universe, a legacy that continues to inspire scientists and scholars seeking to unravel nature's deepest mysteries. His contributions, spanning so many fields, underscore the interconnectedness of knowledge and the profound impact a single, brilliant mind, dedicated to precision and clarity, can have on the advancement of human understanding.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.